In Chapter 6, we're going to be focusing on gases. The kinetic theory of gases describe gases as small particles that move rapidly in a straight line. So if you look at the picture, they're just kind of like billiard balls that go in a straight line until they bump into something, and then they ricochet and keep traveling in a straight line until they bump into something. It also describes gases as having essentially no attractive or repulsive forces. So the gases are so far apart in the container that it's as if that basically the gases aren't going to attract to each other and stick together, because that's what starts to happen when you cool it down and you start turning a gas into a liquid, is then those attractive forces start playing a role, and the gases start sticking together to make the liquid, and then you cool it down further and it makes the solid. So essentially in a gas, they're so far apart that kinetic theory says that you can just assume that there's no attractive or repulsive forces between the gas particles. It also describes the gas as the particles being very far apart. The gas particles have very small volume compared to the volume of the container that they're in. So a gas you might think of, you put gas in a liter and you might think, oh, that gas is filling up a liter. Well, really, on the molecular level, the actual volume of the particle itself is very, very small compared to that liter of gas that you have filled up. And then it also describes gases as being small particles that have kinetic energy that increase as the temperature increases. So basically, if you take a gas and you put it on like say you put a Bunsen burner under it and you start increasing the temperature of the gas, well, what you're doing is you're increasing the kinetic energy of the gas particles. There are 4 different variables that we use to describe the properties of gases. So we're going to focus on the pressure of a gas, and that has the variable capital P. The volume of a gas, which is capital V. So you want to be careful because a lowercase v is usually interpreted as the velocity. So volume has a capital V. The temperature of the gas, which is a capital T, because a lowercase t is usually describes the time. So capital T for temperature, and then the amount of the gas, which we usually give the variable N, because we talk about the gas in terms of how many moles you have. So if you're going to describe a gas to somebody, you usually state what was the pressure, the volume, the temperature, and how much of the gas did you have. So here's a table that I got from your book, and it has some of the definitions. So don't forget to study this table when you're studying for the test, because I might ask you, for example, what is the definition of pressure? And pressure is defined as the force exerted by the gas particles against the walls of the container. So if you have a container, the more force that the particles are hitting the sides of the container with, the more pressure that's going to be exerted by that gas. It has different units, so we talk about pressure in terms of how many atmospheres it has. An atmosphere is abbreviated as ATM. We also describe it as how many millimeters of mercury, how many torr, and how many Pascal. In this particular class, we're not going to use the Pascal unit for pressure, but you do need to get familiar with knowing that a number followed by the unit atmospheres, millimeters of mercury, or torr is describing a pressure. Volume is defined as the space that's occupied by the gas. So it's not the actual volume of the gas particles. It is the volume that the gas is occupying. Some common units would just be any volume units, but in a science class we usually deal with meters or liters and milliliters. Temperature determines the kinetic energy and the random motion of the gas particles. And in a chemistry class, we're usually going to use degrees Celsius and Kelvin, but you do need to refresh on how to convert between Fahrenheit, degrees Celsius, and Kelvin. Kelvin is what is required in the calculations. In this class, however, we're not going to be using any of the gas law calculations. I'm going to take you through the gas laws, and I want you to understand the concepts behind it. But I'm not going to have you do any of the mathematical calculations using those gas laws. So you won't actually have to do the conversion into Kelvin temperature before you use the algebraic formula. But I do want you to know that temperature does need to be in Kelvin for any gas law calculation. Here is the amount of the gas, which defines the quantity of gas present in the container. You can describe how much gas you have by telling me how many grams. More often we talk about how many moles. And if you were going to be using your gas law calculations, I would tell you that you always have to make sure the amount of gas is in moles, but we're actually not going to do any calculations, so you won't have to worry about that. Another property of gases that's very important that you understand, because this one particular property plays a big role in how gases flow through your body. So make sure you get this down. Gases always flow from regions of high pressure to regions of low pressure. Okay, so you might have experienced this if you live out here in Troutdale or in the Gresham region, because we have the gorge, which leads us up to Hood River and the Dalles, and usually it's colder up there in the Dalles and Hood River, and so gases tend to be more dense in cold weather, so they're under higher pressure. So what tends to happen is our air tends to flow from Hood River and the Dalles through the Columbia Gorge and ends up in Troutdale as a quite a big wind that we experience. So that's a result of the fact that there's higher pressure usually in Hood River, lower pressure in Troutdale, so wind is going to travel from Hood River to Troutdale because gases flow from regions of high pressure to regions of low pressure. Atmospheric pressure is defined as the pressure that's exerted by a column of air from the top of the atmosphere to the surface of the Earth. So if you look at this picture, we've got this man standing on Earth, obviously not to scale. And the atmospheric pressure is how much pressure this column of air above him is exerting down on him. Focusing on the air, we'll talk a little bit about this. Air is mainly composed of nitrogen. A lot of students think air is mainly oxygen because we breathe in air and you think that you're breathing in all this oxygen. And you are breathing in quite a bit of oxygen. But if you look at this picture, air is about 78% nitrogen and about 21% oxygen, and 1% of, this is showing 1% of water, but it has a small percent of other gases also. But if you take the amount of pressure being exerted down by a column of air, that gives us our atmospheric pressure. A little bit about atmospheric pressure. So it is about 1 atmosphere. So remember, atmosphere is a unit of pressure. So it is about 1 atm at sea level. So if we look at this picture, we have sea level and then we have some mountains behind it, and it's showing us, the arrow is pointing down because we're talking about atmospheric pressure, and that's exerted down towards Earth. So the pressure, if you are standing at sea level, you can expect that the column of air above you is exerting a pressure of about 1 atm pressure. The atmospheric pressure is going to depend upon the altitude and the weather that day. So if we look at the altitude, if you were to climb this mountain in the back of the picture here, notice that they're showing at the top of this particular mountain, the atmospheric pressure is about 0.7 atmospheres. So basically what I want you to remember, that is, as you climb in altitude, your pressure, the atmospheric pressure, is going to decrease. And that should make sense because the column of air above you is getting smaller. As you climb up, you have less air pressing down on you. Atmospheric pressure is lower at high altitudes where the density of air is less. It is lower on warm days than on cold days. So when I was talking about Hood River and Troutdale, it's often in the winter more cold in Hood River, so the air is more dense. So the pressure is going to be higher where it's cold and lower where it's warm. So it's lower on warm days, higher on cold days. Here's a picture kind of going over how atmospheric pressure changes with altitude. So if we look at our y-axis, on the left side we have altitude in miles, and on the right side we have the pressure in atmospheres. So as I said before, if you are at sea level, so 0 miles above the Earth's surface, the atmospheric pressure is about 1 atm. You only have to go up about 3.5 miles above the Earth's surface and the atmospheric pressure has been cut in half. I find that amazing, that you don't have to go very far up in your airplane before you notice, before the pressure decreases by half. If you get about 7 miles above the Earth's surface, then the pressure is about 1/4 atm. A little bit above 10 miles, then you are at 1/8 of an atm. So you can see from this picture that the pressure decreases pretty rapidly as you climb. Mount Everest is about 6 miles above the Earth's surface. So you can expect that if you're climbing Mount Everest, as you get up there, you're going to be approaching 1/4 of the atmosphere pressure that your body is used to. A barometer measures the pressure that's exerted by the gases in the atmosphere. So a barometer reads your atmospheric pressure. It indicates your atmospheric pressure as the height in millimeters of mercury as a column of mercury. So let's look at this at this barometer here. You start off by having this basin, tub of mercury, and you fill a glass tube all the way to the top with mercury. And then you invert it into your basin of your liquid mercury at the bottom. So a little bit of the mercury is going to fall down depending upon the weight of that column of mercury. So what you're left with here is just a vacuum. So you don't have any air particles at the top of this glass tube. So we don't have to worry about any pressure being exerted by trapped air in here. So basically all that's happening is you have the weight of this column of mercury pushing down. Well, you also have this counter force, where as the column of mercury is wanting to fall and spill out, you also have atmospheric pressure pressing down on this this volume of mercury out here in this basin. So if you are at sea level, then you're going to have 1 atmosphere of pressure pressing down, and as it's pressing down in there, it's going to be trying to push it up the column. So the mercury in the tub is actually going to try to go up your tube of mercury in this column, but you also have the weight of the column of mercury trying to push down. So you have this counteractive force. So you can measure your atmospheric pressure by how high up your mercury climbs in your glass tube. And it turns out that if you have 1 atmosphere of pressure, then the mercury is going to climb 760 millimeters of mercury. Now, normally we look at a millimeter as being a distance unit, and it is, because that's what you're measuring. You're measuring the distance that the mercury has climbed. But once you stick the symbol mercury after the millimeters, now all of a sudden it becomes a pressure unit instead of a distance unit. So if I give you a number with millimeters of mercury, I want your brain to think, pressure. So also I want you to know that 1 atmosphere of pressure is equal to 760 millimeters of mercury, which is what this picture is showing, and that's also equal to 760 torr. I have this conversion for you on your information sheet. So I am going to expect you to be able to convert. I might give you a number in atmospheres and say how many torr is, or how many torr is this? And you can use this conversion or this equality here to kind of set up a factor label process to where you can get your atmospheres to cancel and convert into torr or millimeters of mercury, whatever I want you to convert. So make sure you find this equality here on your information sheet so you'll know how to locate it for your homework and the exams. So why is it they use mercury? Mercury is actually a very dense liquid. So it turns out in this picture, if we look at mercury, at 1 atmosphere of pressure, that mercury column is going to climb 760 millimeters, like we had said. If we used carbon tetrachloride instead of mercury, it's not as dense. It's still fairly dense, but not as dense as mercury. It is going to have to climb 21 feet if you have 1 atmosphere of pressure out here in this basin. Water is going to climb 34 feet. So you'd need a pretty big barometer if you wanted to use water instead of mercury. If you used ethanol, which is less dense than water, it's going to climb 43 feet. So that's one of the reasons you tend to use mercury in your barometers. Here is an example of how important atmospheric pressure is. Normally, if I'm teaching this class face-to-face, I stop here and I pause and I do a little demo on atmospheric pressure and how, if you have an open container, the pressure on the inside is equal to the pressure on the outside. So if you want to pause this video and click on the gas law videos, which in the module is right underneath this video link, you can watch the demo that I normally show before this, and it might make this a little bit more sense. But in the demo, I have a can that is open. So it's just a pop can that's open. And the pressure inside is going to be if I was at sea level, it would be 1 atm of pressure pressing on the outside of the can. And then you would also, if we were standing at sea level, have about 1 atm of pressure pressing in. It turns out that if you decrease the pressure on the inside of the pop can, then the pressure on the outside is no longer going to be equal to the pressure on the inside. It's going to be greater on the outside. So, and that's what happened in this video here. What happened, in this picture, is that the steam cleaners were called in to clean the inside of this rail car. And so they had opened the door and they had gone in and they had cleaned it. But what they had done is, when they had steam cleaned it, that had forced a lot of the air outside of this rail car. And so when they closed it up and they resealed the hatch, there was less air molecules in there. So it was filled with steam, but it had pushed out the nitrogen and oxygen that normally is in the air that fills it up. So when that steam condensed and turned back into liquid water, you had a lot less particles of air floating around in the gaseous state. And so the pressure, because remember, pressure is defined as the force that the particles are pressing on the container, there wasn't as much particles inside this rail card, so you're going to have less collisions with the side of the container. Therefore, the pressure inside became much less when the steam condensed down into water. So as a result, the atmospheric pressure from the outside was greater than the pressure inside the rail car, and it caused this rail car to collapse. There is a concept called Dalton's law of partial pressures. And if we look at this picture, I want you to you might even want to pause the video and look at it and see if you can answer this question. What relationship between pressures of the gases is illustrated above? So what do you notice as you look at this picture? We start off with this tank that just has helium in it. And it's telling me that the partial pressure, or the pressure of helium, is 2 atmospheres. So if we look at the dial, it's telling us this helium is exerting a force or a pressure of 2 atmospheres. In this other tank, we have argon, and it's exerting a pressure of 4 atms, or 4 atmospheres. And they're showing here that putting these two together is going to end up giving us a total pressure of 6 atms. So the relationship that I want you to see is that the partial pressures are additive to get us to the total pressure. If I've got 2 gases in a mixture, all I need to do is figure out the pressure that these pink balls are exerting, and I can add it to the pressure that the purple balls are exerting and add them up together, and that'll give me the total pressure. So showing that kind of mathematically here, I have I thought I had a, right down here on the very bottom. The total pressure is going to be the sum of all the partial pressures exerted by the gases in that mixture. Okay. So the partial pressure of a gas is the pressure of each gas that's in the mixture. It is the pressure that that gas would exert if it were alone in the container. So that's pretty amazing. But if you think about it, there is so much empty space in a gas that, the helium, if I go back to this picture, the pink balls in here, their pressure is not going to change just because I added the purple balls in, because really they don't see each other. There's so much empty space that the pink balls are flying around just as if the purple balls weren't there. So that's what that second bullet's saying. The partial pressure of a particular gas in a mixture is that pressure that that gas would exert even if it wasn't in a mixture. So Dalton's law of partial pressure states that the total pressure of a mixture of gases is the sum of the pressures of the individual pressures. So the individual pressures we call the partial pressures of that. And here is the equation I talked about. So here's a learning check for partial pressure units. Use the factor label method to convert 520 millimeters of mercury into atmospheres, and I want you to record your answer to 3 digits. So I'm going to get my pen. All right, so I want you to use the factor label method. So remember, some of your points are going to be not only attributed to can you get the right answer, but can you show me your correct factor label setup. So using factor label, I'm going to start by writing down the information that's in the problem. 520 millimeters of mercury. Make sure you put the mercury on there. And if you like to put it over 1, that's totally fine. That doesn't matter. That's up to you. Now, I don't want to be in millimeters of mercury, so I'm going to put millimeters of mercury in the denominator of my conversion factor. And the question wants me to convert this to atmospheres, which is abbreviated ATM. And if you look on your information sheet, it tells you that 1 atmosphere is equal to 760 millimeters of mercury. So using that equality, I'm going to put the 760 millimeters of mercury in the denominator and the 1 ATM on the top. That way my millimeters of mercury cancel, and I have atmospheres. When you type that in your calculator, and I told you I wanted it to 3 digits, that's going to be the 0.684 ATMs. All right, so be able to convert between atmospheres, millimeters of mercury, and torr. Here's a learning check on Dalton's law. It says that you have a gas mixture that contains, so I'm going to write this down as I'm reading it along. My mixture contains nitrogen, oxygen, and carbon dioxide, and that exerts a total pressure. So the pressure that's being exerted by my nitrogen plus the oxygen plus the carbon dioxide is equal to 1.58 ATMs. Oh, totally did that wrong. After a sample of hydrogen is added to this mixture. So I start off with a mixture of just nitrogen, oxygen, and carbon dioxide. And then I'm going to add some hydrogen to it, and it tells me that the pressure is going to increase to 1.79 ATMs. And the question is asking me what is the new, no, it asks what is the pressure of the helium. So this is the pressure of the nitrogen, oxygen, and carbon dioxide and nitrogen, or sorry, hydrogen. I'm going to have to start this one over. I totally messed this one. So I'm going to go back. Here's a learning check that's going to use the concept of Dalton's law. So as we read this, it says that you have a gas mixture that contains nitrogen, oxygen, and carbon dioxide, and it exerts a total pressure. So let me write this down. So the pressure, get my pen. So the pressure of the nitrogen plus the oxygen plus the carbon dioxide is equal to 1.58 ATMs. Then they tell you that you add a sample of hydrogen to this mixture. So now we have nitrogen, oxygen, carbon dioxide, and hydrogen. And it tells us that after we add the hydrogen, the pressure goes up to 1.79 ATMs. And the question is, what is just the partial pressure of the hydrogen? Well, using Dalton's law, we know that, I'm going to go ahead and write this in here, that the pressure of the nitrogen plus the pressure of oxygen plus the partial pressure coming from carbon dioxide plus the pressure coming from hydrogen is going to equal the total pressure, which in this case is the 1.79 ATMs. Well, they tell us from before that the pressures exerted by these three added together is 1.58. So if I reduce this down, I've got 1.58 plus that new pressure coming from the hydrogen equals the 1.79. So to get the pressure of the hydrogen, all I have to do is subtract the 1.58 from each side. And that's going to give us 0.21 ATMs, the pressure coming from the hydrogen. So just be able to use this formula of adding up all the partial pressures to get to the total pressure. The air that we breathe, I've talked a little bit about this. It is a gas mixture, so it's homogeneous. Our eyes can't see the difference, so it's just a homogeneous mixture. It contains mainly nitrogen, oxygen, and small amounts of other gases. Here is an example. I want you to kind of focus on the partial pressure and how partial pressures in Dalton's law, how the partial pressures are additive to get the total pressure. So remember, air, if we were at sea level, having a hard time finding my pointer. Back to the arrow. At sea level, we said that the atmospheric pressure was 760 millimeters of mercury. So if you focus on what the partial pressures are, nitrogen exerts about, since air is mainly nitrogen, 594 millimeters of mercury. Oxygen gives about 160 millimeters of mercury. Carbon dioxide is about 0.3. Water vapor 5.7, and if you add it up, according to Dalton's law, partial pressures are additive, so that gives us our total pressure of 760 millimeters of mercury. So gases, to kind of talk about this, I want to remind you that gases flow from regions of high pressure to regions of low pressure. So in the lungs, oxygen enters the blood while carbon dioxide from the blood's released. So let's look at this picture for a second to get our bearings. Here's the lungs that they're showing in the picture. And out here is the atmosphere. So you're breathing air into and out of your lungs. Then it goes into the heart, and then they're showing it over here. We have the tissue cell. Okay, so our first thing is saying that if we focus on the pressure inside our lungs, so let's focus on oxygen first. Inside our lungs, there's a pressure of oxygen about 100 millimeters of mercury. Outside, the pressure of oxygen is 160. So which way, when you open your lungs, does oxygen tend to flow? Well, oxygen is going to flow from the outside to the inside because there's higher pressure of oxygen outside than inside. If we focus on the carbon dioxide, we've got 40 millimeters of mercury inside our lungs and only 0.3 on the outside. So when our lungs open up, carbon dioxide is just going to naturally leave our lungs because we have higher pressure on the inside. If we focus on the heart, well, I'm not going to take the time. You can look at this and kind of prove to yourself that gases flow from regions of high pressure to low pressure. The next bullet here in the tissues, oxygen is going to enter the cell while carbon dioxide is going to leave the cells and enter into the blood. And all of this has a lot to do with the pressure. So inside the tissues of our cell, remember that the metabolism, our cell, is using up oxygen and then producing carbon dioxide. So we have a high pressure of carbon dioxide inside those tissue cells because they're generating the carbon dioxide. So this slide is showing that the partial pressure of carbon dioxide is greater than 50. And if you look at the pressure inside the blood, it's about 40. So carbon dioxide is going to leave the tissues and into the blood because there's a higher pressure inside the tissues. Oxygen is going to go the other way. You don't have much oxygen inside your tissue cells because they're continually using it. So here it's showing that our oxygen's partial pressure is 100. It's less than 30 inside the tissues. So oxygen is going to go from the blood into the tissues because of the higher pressure. So this is focusing still on the blood gases. It's kind of bringing in the same point that in the body, oxygen flows into the tissues because the partial pressure of oxygen is higher in the blood, lower in the tissues. It's kind of what I just talked about. Carbon dioxide is going to flow out of the tissues because the partial pressure of carbon dioxide is higher in the tissues, lower on the outside. Okay, talking about Boyle's law. We're about to enter a section where we're talking about gas laws, and there's a lot of different relationships between gases and those four variables. You remember the four properties that describe a gas: the pressure, volume, temperature, and the amount of moles of gas that you have. And there's a lot of gas laws that are derived from the relationship between those four different properties. Boyle's law is one of them. Once again, to remind you, your book might take you through some of the calculations using these equations I'm going to show you, but I'm not going to in Chem 103. We're just going to make sure you understand the concepts behind it. So, looking at this cylinder with a piston, we start off with the cylinder on the left, and we have a volume of 4 liters, and the atmospheric pressure is 1 atm. If I push down on this cylinder, my volume is decreasing, and according to this picture, it looks like I've cut the volume in half. I've gone from 4 liters down to 2 liters. Well, look what happened to the pressure. It went from 1 atmosphere of pressure up to 2 atmospheres of pressure. So what relationship between pressure and volume is being illustrated here? I want you to know this. So I want you to be able to tell me, is the relationship that pressure and volume are directly related or they're inversely related? And I want you to be able to tell me that they are inversely related. If volume goes up, the pressure is going to go down. And opposite, if volume goes down, the pressure is going to go up. So that's an inverse relationship. So make sure you know that. It turns out that the product of the pressure times the volume is always constant, assuming that you don't change the amount of moles of gas you have or change the temperature. Okay, so if you hold constant the volume of gas and the temperature of gas, then, or did I say that right? You hold constant the moles of gas and temperature, and you have a container with a particular, at a particular pressure and volume. You can change the pressure, and the volume is going to change in such a way that their product is always constant. So pressure and volume are inversely related. So if you think about a bicycle pump, as you press down on the handle, you're decreasing the volume, so you're increasing the pressure, which is going to increase the pressure inside your tires. At constant moles and temperature, as the volume of a gas decreases, the pressure is going to increase. And the opposite will be true. If the volume increases, the pressure is going to decrease. So here is how using Boyle's law works inside of our lungs. So let's go over this picture. We start off with our lungs, which are connected to a diaphragm. And when you inhale, what's happening is the diaphragm is contracting. And as the diaphragm contracts, it causes the diaphragm to move down. And what happens to the volume of the lungs, the space of the lungs, if this diaphragm moves down? And I'm hoping you can see that that's going to expand the lungs. You're going to have more volume. The opposite's true if we look at the picture on the right. When you're exhaling, what's happening is the diaphragm relaxes. As when the diaphragm relaxes, it moves up. Well, what happens to the volume of the lungs when the diaphragm moves up? And the volume of the lungs is actually going to decrease. So when you're breathing, what happens is the diaphragm contracts, causing it to move down, causing the volume of the lungs to increase. And here's the important question I have for you. If my volume increases of the lungs, what happens to the pressure inside the lungs? Volume gets bigger. I hope you would say that the pressure is going to get smaller then, because they're inversely related. Bigger volume, smaller pressure. So if my pressure decreases inside the lungs and my pressure on the outside stays 1 atmosphere pressure, which way is the air going to flow? Well, air is going to flow from higher pressure to lower pressure. So our air is going to move inside. As the diaphragm contracts, air is moved inside because the pressure is greater on the outside. The opposite's true when you exhale. The diaphragm relaxes, causing the diaphragm to move up, making the volume of the lungs smaller. If volume decreases, pressure is going to increase. The pressure then is going to be higher inside the lungs, so then air is going to move out. The second gas law we're going to focus on is called Charles' law. You do not need to memorize the name of these laws. So if we look at the piston, I'm going to sneeze. Excuse me. Okay, it passed. If we look at the piston on the left, the temperature is 200 Kelvin, and the volume they're showing is at 1 liter. If we heat it up, now the piston's free to move in this case. Okay, so the piston can move freely up or down depending upon the pressure. Actually, I need to restate that, because in this example, since we're focusing on temperature and volume, pressure and the amount of moles has to stay constant, okay? And since the piston is free to move, that implies that it's going to be at whatever the atmospheric pressure is. So if we pretend we're at sea level and we say that the atmospheric pressure pressing down on this piston is 1 atm, it's also going to be 1 atm here. So the pressure and the amount of particles we have is staying constant. So we start off with a temperature of 200 Kelvin. The volume is 1 liters. If I crank up the heat and I double the heat to 400 Kelvin, what happened to the volume? The volume also doubled. So if I asked you what is the relationship between temperature and volume of gases, assuming you're holding pressure and moles constant, then I would like you to say that they are directly related. If one goes up, the other one goes up. And notice that they also go up by the same magnitude. If I doubled the temperature, I doubled the volume. So because of that, the volume divided by the temperature is always going to be a constant. If we go back to that previous slide, if I take well, let's invert it for the sake of this example. Temperature divided by volume here is going to end up being 200. 200 divided by 1 is 200. If I do the same over here, 400 divided by 2 is 200. So no matter what ratio I'm setting up, as long as I keep pressure and moles constant, I'm always going to have the same answer for the volume divided by the temperature. For calculations, the volume, you have to use Kelvin temperature, and the volume and the Kelvin temperature are directly related. If one goes up, the other goes up. If one goes down, the other goes down. So at constant moles and pressure, if the temperature increases, the volume is going to increase. So focusing a little bit more on the temperature scale, we went over this the first lab in recitation, but we're going to go over here again. Temperature scale is, there's 3 different temperature scales often used: Kelvin, Celsius, and Fahrenheit. In a science class, or in the real world in sciences, scientists pretty much stick with Kelvin and Celsius. All three of these scales have a reference point for the boiling and freezing point of water. So if we look at it, Celsius I think is the easiest because water freezes at 0 degrees Celsius and boils at 100. That's pretty easy to remember. Here in the United States, we're pretty familiar with the fact in degrees Fahrenheit, water is going to freeze at 32 degrees Fahrenheit, boils at 212 degrees Fahrenheit. Going to the Kelvin temperature, water is going to freeze at 273 Kelvin, boil at 373 Kelvin. Notice the difference between freezing and boiling point in the Kelvin and Celsius scale. So 100 minus 0 is going to be 100. So the difference between freezing and boiling in the Celsius scale is 100 degrees. And between Kelvin freezing and boiling is 100 Kelvin. So the tick marks are the same distance apart in the Celsius and Kelvin scale. In order, the difference between freezing and boiling in the Fahrenheit scale is 180 degrees. So 0 Kelvin is what we call absolute zero. And you have this formula on your information sheet. I want you to remember how to use it, because I'm going to be asking you to convert between Celsius and Kelvin and the Fahrenheit again. So how do we know there is an absolute zero? How do we know there's such a thing as the absolute zero temperature, and what is that value? So if we look at this graph, and we've got temperature along the x-axis and volume along the y-axis. As you decrease in temperature, what's happening to the volume? Your volume is getting small. And at some point you're going to get down here to 0 Kelvin, and that is when you're going to supposedly have 0 volume. Now 0 Kelvin is a theoretical temperature. We've never actually been able to get to 0 Kelvin. We've gotten very, very, very close, but we've never reached it, and technically we should never be able to reach it, because at 0 Kelvin we're going to have a 0 volume. And is that possible? I mean, for a gas you can compress it down pretty small, but will you ever get to where you have a 0 volume? No. So the volume of a gas gets smaller as the temperature decreases. Matter cannot have a negative volume, so absolute zero is the temperature where the volume of the gas equals 0. So the question up here, what is the value of absolute zero? Well, that would be 0 Kelvin. So go ahead and write in here absolute value equals 0 K. So what is the value of absolute zero in degrees Celsius? I'll get my pen for this. So using our formula, absolute zero we said was 0 Kelvin. Notice they don't use a degree symbol for Kelvin. They put that little degree symbol for Celsius and Fahrenheit, but not for Kelvin. So they want us to convert 0 Kelvin into degrees Celsius. So we're going to plug in 0 Kelvin here. So 0 for the Kelvin. We're trying to solve for the degrees Celsius, and we have 273. So to get degrees Celsius by itself, we're going to subtract 273 from both sides, and that's going to lead us with negative 273 is what the degree Celsius is when you're at 0 Kelvin. The last gas law we're going to look at is called the Gay-Lussac's law, and that is going to look at how temperature and pressure relate to each other if you hold the volume and the moles constant. So looking at this, let me get my point arrow back. Our first cylinder, in this particular case, pressure is, okay, I'm going to change my thought process here. We start off with the temperature at 200 Kelvin and a pressure at 1 atmosphere. And to make this make sense, in this case our piston is not free to move, okay? So we're holding our piston constant or glued at this height. So the temperature, 200 Kelvin, 1 atmosphere pressure, I double the temperature, I crank up the heat to 400 Kelvin. What happens to the pressure? Well, the pressure is also going to double. Remember, the pressure is defined as the force exerted by the particles along the inside of the container. So what's happening is you heat it up, or why don't you tell me, what happens to the kinetic energy of the particles when you increase the temperature? If you increase the temperature, you increase the kinetic energy. So these gas particles start to move around with more kinetic energy. So they're flying around with more energy, so it should make sense that they are going to be hitting the sides of the container with more force. Other collisions, hit stronger collisions. So double the temperature, you double the pressure. So what is the relationship here? I'd like you to tell me that it is directly related. If temperature goes up, pressure goes up. Temperature goes down, pressure is going to go down. And because of that, since they're inversely related, if you take the pressure divided by the temperature, and if you're holding the volume and the moles constant, then as you change the temperature or the pressure, the other is going to adjust in such a way that when you divide one by the other, it's always going to come out to be the same number. So pressure and Kelvin temperature are directly related. If you hold the moles and the volume constant, if you increase the temperature, you increase the pressure. Okay, so the last two slides here are just kind of practice to make sure we understand some of the concepts. So let me get my pen for this. You might want to pause the video and see if you can answer these next two slides by yourself. So I am going to start off by just going down 1, 2, 3, and 4 just to kind of refresh myself with this. So 1 is going to be gases can be compressed easily. So you can start off with a particular volume and it's easy to push a piston down and compress the gas. Next one, number 2, gases expand to fill the volume of the container. 3 is gases have a very low density. So remember, density from the beginning of the term is your mass divided by your volume. So gases have a very low density. They have a very big volume and they're very light because there's not very many of them in your container. And then 4 is gases can diffuse through each other. So gases can just fly right by each other and not even realize that each other is in there for the most part. Okay, so those are the ones we're trying to decide on here. So our first one, because gas particles are far apart, they can easily be squeezed close together by an outside force. So you can push down on the piston and squeeze the gas together. So that's going to be number 2. No, sorry, that's number 1. Gases can be compressed easily. The next one, gas particles are constantly moving and are separated by large distances. This leads to freedom for the particles of one gas to move through the empty space of another gas. So that would be number 4. Gases can diffuse through each other. The next one, gas particles are constantly moving with no attractive forces between the particles. So they will expand until they meet the outside, an outside force, namely the walls of the container. So basically, since the particles aren't sticking, they're not forming liquids and solids, so they're free to hit the outside of the containers. So they're going to expand until they fill their container. So that's going to be number 2. Since they're not sticking together, they're free to just expand. The last one, because a gas is mostly empty space, there are few particles, so a very low mass per unit volume. So right here, low mass is going to lead to a low density. So that'll be number 3. On our next slide, 5 is the gases exert a pressure on the container of the walls. That's just our definition of pressure. Boyle's law is relating the fact that the pressure and volume are inversely related. Charles' law, volume and temperature are directly related. And Dalton's law states that you can add up the sum of all the partial pressures will equal your total pressure. Okay, so the first one here, moving gas particles collide with the container walls, thus exerting a force on every square inch. So that is our definition of pressure. So that would be number 5. Particles collide with the container walls. When the volume of a gas is decreased, okay, so I'm just going to make myself some notes here. Volume decreases. The particles collide with the wall more often, leading to a greater pressure. When the volume of the gas increases, the particles collide less often, decreasing the pressure. So pressure is going to, wait, let me read this again. When the volume, okay, I have to rephrase this. The volume increases, pressure decreases. So volume increases, pressure decreases. We're talking about Boyle's law here, that pressure and volume are inversely related. Since the particles move independently of one another, each gas mixture will exert a pressure independent of the pressure of all the other gases. The total pressure will be the sum of the individual pressures. That's Dalton's law. So that's number 8. And then our last one, increased temperature causes the particles to move faster, leading to more and harder collisions with the walls. That's a typo, that should be walls. Pressure inside the walls is increased until the volume expands to the point where the pressure inside the walls again equals the pressure on the outside. So pressure inside the walls increasing the temperature, increasing the temperature causes more collisions, so that's going to increase the pressure. So that is, actually, I do not have that one, so I must be reading this wrong. Increasing the temperature causes the particles, I'm going to restart this one because I'm just messing this up. So let me go back. Let's see. Okay, 6, gas exerts a pressure on the container walls. So that's our definition of pressure. Actually, that was 5. 6 is Boyle's law, which is relating the fact that pressure and volume are inversely related. 7 is Charles' law, and here they're focusing on volume and temperature being directly related. And number 8 is Dalton's law of partial pressure, which is you can add up all the partial pressures and that's going to give you the total pressure of a mixture of gases. Okay, let's read the first one. I got to go back and get my pen. Moving gas particles collide with the container of the wall, thus exerting a force on every square inch. So that is our definition of pressure. So that will be number 5. This next one here, when the volume of a gas decreases, so you decrease the volume, the particles are going to collide with the walls more often because you have less volume, leading to a greater pressure. So decrease the volume, increase the pressure. So when the volume of a gas increases, so now we're going in the opposite direction. If you increase the volume of a gas, the particles are going to collide less often, leading to a decrease in pressure. So decrease the volume, increase the pressure, or increase the volume, decrease the pressure. So that is talking about that pressure and volume are inversely related. One goes up, the other goes down. That's Boyle's law. Once again, I'm not going to expect you to memorize that it's called Boyle's law. Just know that pressure and volume are inversely related. The next one here, since the particles move independently of one another, each gas in the mixture will exert a pressure independent of the pressure of the other gases. So the total pressure will be the sum of the individual pressures. That is Dalton's law. The total pressure is the sum, oops, ran out of room, sum of your individual pressures. Individual pressures are also called the partial pressures. Okay, let's read this next paragraph. If you increase the temperature, you're going to cause the particles to move faster with more kinetic energy, leading to more and harder collisions with the wall. This is actually a typo. That should be walls. So increasing the temperature, you're going to have more collisions. Pressure inside the walls is increased until the volume expands to the point where the pressure inside the walls is again equal to the pressure outside. So this last part right here is telling us, is explaining that the pressure is being held constant. So we must have that free moving piston because it's telling us that the volume is going to expand until the pressure, is equal again to what it was on the outside. So we have a free moving piston. So let's kind of get that image in our head. We have a container with the gas in it. We got our piston. We're going to increase the temperature, which is going to increase the kinetic energy, so they start forcing the piston to move up. So what is happening to the volume here? So if I increase the temperature, let me underline that. Increase the temperature, particles are going to collide, causing the volume to expand because the pressure is going to stay constant. So if you increase the temperature, volume is going to increase. So that is our Charles' law, that temperature and volume are directly related. If one goes up, the other goes up. Alrighty.